So let's start. Thanks for coming to the talk. We're going to talk about type erasure. And the goal of this talk is basically so that, like, if I succeed at the end of the talk, you will say, of course, this is so obvious. Why did we need to talk about it? That's kind of the ideal outcome. So we're basically going to talk about what it is, how it's used, and how it's done. This is one of easily found sort of canonical definitions of type erasure. This might have been from Wikipedia, but these descriptions are what you would typically find if you Google for type erasure. It's a programming technique by which the explicit type information is removed from the program. So basically, type erasure is when you erase the types. That, of course, explains everything. There is the second definition, which is, in my opinion, kind of more accurate and easier to understand. They're both about equally informative. So now the first definition is technically correct, which is the best kind of correct. Okay. Fellow nerds got the reference. So a program that is written in a strongly typed language but doesn't use the type that has been erased, so how does this actually work? Well, it's some kind of abstraction. So first, let's see how it looks like. So I'll just show you what a program that employs type erasure looks like, and then I'll explain what's actually happening under the covers. So we'll start with a non-type erased program because I'm going to contrast the two. So here is a unique pointer. Now, the deletion is not explicitly visible. In fact, nothing here tells you how the deletion will take place, but it's done by calling a callable object std default delete, which actually calls operator delete. Okay, so this is the default. If you wanted a different deleter, what would you do? So you have some heap, you have allocate, deallocate, and let's say you want to allocate from that heap. You would write a custom operator new that allocates from that heap. If you have that operator new and you pass the heap pointer, then that's what will be used for allocations. Notice that you actually don't have operator delete with arguments. You can write one, it will compile, but you can't invoke it. So, in order to actually delete this, you have to do something else, which is you have to write your own deleter, which has operator paren. It's callable. It will delete your deallocate. Well, it doesn't call destructor. It only has to deallocate memory. So it will deallocate memory the right way. And how do you hook it up to the unique pointer? You pass it as a constructor argument, but the unique pointer changed the type. The deleter is the second template argument to the unique pointer template. So this works, no gotchas here. This is exactly what you should be doing with unique footer if you want a custom deleter. What does the deleter do, the operator paren? Well, invokes the destructor and then deallocates the memory. Destructor has to be explicitly invoked because you can't call operator delete with arguments. Okay, yeah, there are some restrictions. It has to be no-zero movable, but that's fine. Notice that unique putters with different deleters are explicitly different types. So for example, you can't assign from one to the other. You cannot initialize a unique putter with one deleter with the constructor matching a unique putter with another deleter. None of this will compile. The errors you will get will be something about the two unique putters being different types, and they are. You can actually deduce deleter type. If you have a unique putter object, you can interrogate it and find out what the deleter type is using metaprogramming, or there are many ways. But the deleter type is embedded in the unique putter type. Now let's look at the shared pointer and contrast it with unique pointer. So if you don't specify any deleters, they look exactly the same. If you do specify a deleter, there is a big difference. Constructor actually looks exactly the same. You pass the deleter to both constructors. But in the unique putter, that deleter is also, the type of that deleter is the second template argument, whereas in the shared putter, there is no mention of the deleter in the type. So if you have an object of type of shared putter, you cannot deduce which deleter was used to construct it, because the type of all shared putters was the same data type int, but different deleters, all these shared putters have exactly the same type. So the deleter type has been erased. That's what it means to erase a type. So from this, this is the last mention of the deleter type in your code. From this point forward, you won't see this type again, as long as you're dealing with the shared putter. So two shared putters with different deleters, they are the same type, they're assignable. Now this doesn't prove that they're the same type. You could write an assignment operator for different types, but they are the same type. At the same time, at the end here, when they go out of scope, the correct deleter will be activated and executed and delete your object the right way. Even though it's not part of the type. Both of these shared pointers have exactly the same type. They have different deleters, and somehow the right deleter is called. So erase types are not explicitly visible, but not forgotten either. They're hidden somewhere. So, okay, this is what it looks like. Why would you want to do this? Several reasons. So I'll show you kind of examples from two reasons that gives you the idea. The kind of ultimate type erased object in C++ is stud function. Well, one of them, so stud any is another one. So stud function is it's the template, but it's instantiated on a type that is a signature of a callable. Takes a string by const reference, returns size t. That's all that you know. If you have a stud function object, the only thing you can find out about it is that it's callable with that type. Who provides that calling capability? Anyone. Freestanding function? Sure. Lambda, even state lambdas with captures that do not decay to freestanding functions, go right ahead. Member function pointers, no problem. That too. So now our stud function f has only one type, and somehow we can stick all these different types into it, and it'll do the right thing. But if you look at it from the design point of view, what it does is it abstracts away all the behavior of the type you erase, except the set of behaviors that you consider relevant. It's a very flexible abstraction. You decide what's relevant. In my case, I say what's relevant is I can invoke this type with a string and I get back size t. That's the only behavior of this type that to me at this moment is relevant. All other behavior, well, for stud function they have to be copyable, but basically ignoring that, like all other behavior is abstracted away. So fundamentally, type erasure is a kind of abstraction, is an abstraction technique that allows you to separate the interface from implementation. And when we talk about interface, it's actually a subset of the interface. It's a subset of the interface that we deem relevant for our particular problem. Now, inheritance does the same thing, but inheritance is significantly less flexible. First of all, with inheritance, what the interface you inherit is, that has to be the whole interface. You can separate it from the implementation, but you don't get to pick and choose like half of the interface. You take that whole thing. Second, it's much more intrusive. You can't take some other arbitrary class that happens to have the same interface and say, I want to use it through inheritance. No, you have to derive it from that base class. So Type erasure is a non-intrusive or sometimes called external polymorphism. Your types that you use don't have to be designed for that kind of polymorphism, whereas inheritance, types that you use have to be designed from the ground up to support inheritance. They have to be part of that hierarchy. So that's what type erasure does from the design point of view. It's an abstraction that separates some elements of the behavior from all other properties of the type, and it's non-intrusive or external. It also can be used mostly as an implementation technique. So it's used for decoupling dependencies. So let's say you have in your application, you have a network and you need the network class. So you have a network class, it has the send and receive. And yeah, it's really that easy to write network classes. We all know that. So it's used across your entire application. But one small part of your application needs encryption on the traffic. Oh, and another small part of your application has to deal with bad networks, so they need error correction codes. So what you decide to do is basically create a processor of data. So when you send, your client just say, send this data. Inside the network layer, you're going to apply some processing like encryption or add error correction code, and then you're going to say, send that. The problem is that now your entire application depends on those processors because their types are somewhere explicitly embedded in the network code. So that just created a huge dependency, and if you own, let's say, that encryption, you just became the most hated person in the entire organization because anytime you do anything, everybody has to recompile. So one of the ways to solve it, not the only way, but a simple and elegant solution, is to use the type erasure. Network will not depend on the processor type. Inside the network, we're going to use, let's say, std function that whatever the right signature is, let's say, for simplicity, I'm just saying all my buffers are char star. So takes a char star, returns a char star, and the default processor is do nothing. And in my send, I apply the processor to the data. The default processor is do nothing, but I can install my own custom processor, and what it will do is it will take a callable, and yeah, I'm omitting all the restrictions. So yeah, you want error messages to be better, so you want this thing, if you give it a wrong object, you want decent error message. I'm omitting all requires, all static asserts. I'm just showing you kind of the bare essence of this. So you will give it a callable. The callable will be assigned, so installed into this function, and next time you call send, that processor will be invoked. Well, yes, I'm assuming that there is only one processor at any given time, but that's a design mechanic. I'm basically, even you could have multiple processors, but that's, I'm not talking about network design. The point is that this entire generic code is completely agnostic of the processor type, and yet I can have my processor types written and installed into this network. If I need to change my processor, nobody has to recompile except me.
It'd be better putting that in your constructor.
Sorry?
It'd be better dropping that dependency in your constructor.
Well, it depends if I need to install it after the fact, or like maybe I need to install the processor at a certain point. Like so, these are design decision things. And I would probably have like multiple network.
I just gave a talk about not to do that. That's why I bring it up.
Well, so this is a design decision, and it depends basically. If there is only one network object for everything, you would. Well, you have a bigger problems to deal with processors, but you would be installing and removing them. So if you look at it from the design pattern point of view, it's actually a strategy pattern. So the strategy pattern is where an implementation of a particular behavior can be chosen at runtime, and here it is. I have my network, and I'm saying that for now the processor is going to be this. So this is the type erasure as a design pattern, as an abstraction, or as a purely implementational aid to decouple dependencies. So I've shown you what it looks like. I've shown you what it's used for. Now the really interesting part is how does it actually work? You have actually seen this before. Anybody here programmed in C, not C++, but C? Okay, so you've used Type Erasure before. This is what Type Erasure in C looks like. So I have this qsort. This comes from the standard C library. Takes void star, takes size t, and takes a comparison function. And the comparison function takes void star. It is used to compare whatever types you're actually sorting. Notice that in this code there is, and inside, if you look at the implementation of this qsort, there is no mention of the type that you're going to sort. Here is how you call it. So you have, let's say, an array of int. You call it array count. At this point, at the call side, this is the last time in your execution flow where you have the mention of the type int. From this moment on, there is no mention of int in this entire sorting process. So what do? We extract some relevant property like size, and we pass in the comparison function. But the comparison function, so at this point I know that I'm comparing ints, but the comparison function is restricted to this typeless interface. So what do? My signature is fixed, but I know what I'm writing this for. So inside the function, I'm going to recover the type information, even though the signature is typeless. So this is basically the entire type erasure mechanism is seen right here. The type is known at the invocation point, and that's the last time it's known. At that point, I decide what I'm going to pass in, and what I'm going to pass in as arguments depends on the type. I'm passing some type-dependent information into the generic code, but the type is hidden not anywhere in the declarations. It's actually hidden in the code that is being generated for this function. So, and the code depends only on the relevant type properties, whatever they happen to be. Whatever I need to use here, that's the type properties I care about. All other properties, and obviously the size in this case, all other properties of this type I don't care about. So this is the type erasure in C. So again, the essential elements. General code does not depend on which type we're sorting. Only on some relevant type properties, which is size. It needs to know basically how to jump through the array, and the rule for comparing. All interfaces are completely generic. There is no type information in them. At the call side, I extract whatever type properties I need and pass them to this generic code. All other information is erased, including the name of the type itself. Name of the type isn't one of the relevant properties, so that is being erased along with all other irrelevant properties of the type. And I still need to perform a type-dependent action at some point. So I have to generate some code that has a typeless or type-agnostic interface, but the code itself is aware of the types. This act of recovering the type from typeless information is called reification. So this function performs the reification and executes type-dependent code. Reification in C is manual. There is no compile time or runtime error detection in this. The only thing, and it's a big thing, but from the understanding point of view, you have to understand that the only thing C++ adds to this is the ability to generate these functions, these reification functions, such that they're correct by construction, or you get compile time errors if they're incorrect. That's all C++ brings to the table. Other than that, this C model of reification is what we use in C++, of type erasure and reification. So now we're going to see how C++ does it. But the important, the essential part to understand about the type erasure from all of this is the type, obviously, it's not lost completely because you have to perform, somewhere in your generic code, you have to perform type-dependent actions. That type is hidden in the code of some function or basically some piece of code that in the execution of this code, in the body of that function, type information is present, but in the interfaces it's not. So that's basically how type erasure is organized. In C, you have to write this code manually. In C++, we make the compiler generate the correct by construction code. So now let's see C++ version of it. A question? No? Okay. There are three main ways to do it in C++. There are lots of variations, but they boil down to one of these three approaches. You can do it using inheritance, the regular inheritance virtual functions. You can do it using static functions, and you can do it using vtable. And if you think that vtable and inheritance are the same thing, I'll show you what I mean by that when we get to that type.
There's also switch and opcode. Which is how stud function works.
Switch and opcode is just an inefficient implementation of a vtable, basically. Now, stud function doesn't have to work that way.
It doesn't have to.
Nothing requires it to be this way. And actually, like the one which comes with GCC does not have a switch and opcode. It uses a very bad implementation of this second strategy. So we're going to use the shared pointer as example, and we're going to focus on the deleter because that's the erase type. So we're not going to deal with the shared ownership at all. So basically, our smart pointer, which we're going to call it smart pointer, our smart pointer is basically is the same as a unique pointer, only it uses type erasure instead of explicit types. That'll be our working example. But if you use a shared pointer and you never use sharing, that's basically what you get. Unique putter with an erased deletion type. Okay, let's start with inheritance. So here is our type erased smart pointer. It's a smart pointer, so it hides the pointer to the actual data. It has all the smart pointer operator stuff. It has the constructor from the pointer, and the second argument, as we have already seen, is the deleter. Something happens in the constructor on the account of the fact that deleter is present. We don't know what yet. In the destructor, the correct deletion is done. So in the destructor, we have to employ this particular deleter, or its copy actually, even though nothing in this type itself depends on this type deleter. There is a template constructor, but nothing in class smart putter depends on the deleter. If I give you an object of class smart putter, you cannot deduce what the deleter was. It's nowhere in its type. Okay, so template is of only one parameter. The last place where you know what the deleter is the constructor. So this is where you have to do something. This is your last opportunity to perform an action that depends on, explicitly depends on the deleter type. So we already know that the deleter type in type erasure is hidden somewhere in the code. So at this moment when you're doing the constructor, you have to generate some code that has type agnostic interface, but type-dependent implementation. So let's see how we're going to do that. The code isn't very complex, but the full thing doesn't fit on the slide, so we're going to go through it piecemeal. We have a base class, and this is actually happening inside our smart pointer. So I'm not showing you that around all of this is the template of the smart pointer itself, but this is all happening inside the smart pointer. So we have a base class which has the interface for the properties we deem relevant. Again, we're abstracting away everything except the relevant properties. And there are only two relevant properties that we care about. One is how do I actually use this thing to delete something? That'll be operator paren. Notice that the interface is type agnostic, void star. And the second is, okay, how do I delete? I have a copy of the deleter somewhere in my smart pointer. How do I delete it? Okay, these are the only two things we deem relevant. Everything else is abstracted away. Now I have a template class which inherits from this base, and it has to override. So first of all, it has a constructor, and the constructor saves. This template explicitly depends on the deleter type. The constructor saves that deleter because deleter is a template parameter of my template. I can have member variables of that type, so I'm going to save the deleter. And then my operator paren, the interface is fixed. Even though I know what the deleter is at this point, I can't use it here because it overrides this function. But I can reify the type.
Where did T come from?
Yeah, I think you mean deleter.
No. I'm casting. No, deleter is explicit. Deleter is right here.
T, sure.
Oh, so remember, this whole thing is inside the smart pointer template, which didn't fit on the slide, but this whole thing is inside the smart pointer template. So any nested classes inside a class template have direct implicit access to the template parameters of the containing class. So T,
if
yeah.
that's the case, why do you need void star?
Because this is the base function.
Except that T should be known.
You could use T, yes. You can use T
If it's in.
Oh, okay,
unless you
I can use,
outside.
yeah, okay, I could use T here, right? Okay, I could use T here. I can't, yeah, you're right, I could use T. I just can't use deleter. Okay, you're right. Yeah, I can use T. Okay, but the deleter type is here, but not here. Yeah, I can use T.
That generates a lot more classes, though.
Well, if it's
you use
already.
the slot.
Well,
It's a nested,
having
it's a
full
nested class. So I don't know if it generates more code or not, but
It doesn't, but you could pull destroy base outside your pointer, so you had only one base.
I could pull destroy base outside, and then I would have it. So this could be not a nested type. This can be actually fully generic and live outside of my smart pointers if I wanted to do that.
Or you can do it half-half.
You can, yeah, you can put the base outside, but the template inside. Yeah. Anyway, so that's yeah. You can do this. So now, okay, I'm going to put this inside my smart pointer class. I have the T explicitly, and now the code doesn't fit on the slides. So this is my destroy base, was what we saw on the previous slide. This is my template derived class, with what we saw on the previous slide. Constructor is the one that has to tie everything together, because the constructor is the last place where I have access to this deleter type. So yeah, I take the T star, I take the deleter, and inside my class, my smart pointer, I'm going to have a pointer which is destroy base. It's a base class pointer, does not depend on the deleter type. I can initialize it with any derived class. So the derived class that I'm attaching, that I'm hanging on this pointer, knows what the deleter is. The base class doesn't. So as you can see, this is the last line in the code where this deleter type is explicitly visible. In the destructor, where I get to use it, I invoke this through the virtual function. Deleter type is not visible anywhere here, but the right action happens because the code that the compiler generated for the derived class knows what the deleter type is. So in the constructor, we basically instantiate a template that reifies the deleter type. The interface doesn't mention anything about the deleter, but the destructor uses it through the polymorphic function. So you can say that the deleter type is encoded essentially in the virtual pointer of whatever this this object is. Okay, now shared putter accepts a default deleter. If I don't specify any custom deleter, you get the default deleter. Let's say I want to do that too. There are two ways to do it. One is to leave the deleter pointer null, that this pointer here, you can just leave it as null. And then in the destructor, you would have to check if the pointer is null, then use default delete, otherwise use the custom delete. Bad idea, because you have that null check even if the custom deleter is installed, and you don't need it. Much better is to say that it's never null. It's initialized with the default action. So we always invoke the deleter through that type erased interface. And the default just does the default thing, whatever the default thing is. The rest of the code keeps the same logic. So there is no if condition, and also there are no branches in the code logic. The code logic is always the same. I don't have a separate logic for the default deleter. Now, there are multiple type erased classes in standard C++. So shared putter erases the deleter. Stud function erases everything except the callable signature. Stud_any erases everything. Typically, the constructor is a template and deduces the type that we're going to erase. In something like stud function, also assignment operators can do it. For a smart pointer, it's a deleter type. If we're using the inheritance-based implementation of type erasure, the constructor will create a derived object with overrides that are aware of the type we are erasing, like the deleter. But the interface comes from the base class, and the base class is not aware of the type we are erasing, so the interface has to be completely type agnostic. You might have casts involved. And if you need a default value, for shared putter, we want to have a default value. In some other type array situations, maybe you don't want a default value, then you just don't allow it. But if you need a default value, the best way to implement it is to initialize your action, your base class pointer, to the default, to the action of the default type. Okay, we focused on the relevant properties, but we didn't actually cover all the relevant properties, because you might have to copy this entire object, including the deleter that is hidden somewhere in there. You might have to move it, you might have to compare them. So for copying, you would just, if you're using this inheritance-based implementation, you would have to give your base and derived class a virtual function to clone itself and override it to clone correctly. For moving, you have two options depending on what you want to moved from state to be. You can simply transfer the ownership of the deleter, or you can implement a move me function that would actually move the right way on the derived object and leave the deleter in a moved from state. It depends on what you want the moved from state to look like. For the comparison, again, you have a choice. So in particular, shared putter compares for equal even with different deleters. They only look at the addresses. If you do want to compare the erase types, then it's yet another virtual function. So all the aspects of behavior that you deem relevant, and previously I said there are only two relevant ones, how to use the deleter and how to delete the deleter. In reality, unless your object is like non-copyable or non-movable, copying and moving and maybe comparing are also relevant behavior elements. So whatever behavior elements you deem relevant, in this approach you create a virtual function for every one of them. And in the derived template, you override every one of them with the correct action for your deleter type. And all of them would have to reify the deleter type. Okay, before we go to the next implementation, I'm going to show you a few more enhancements you can do on it. They apply to all three type erasure implementations. I'm just showing you on the first one. So one of the big problems with this type erasure mechanism is it's really slow, and it's slow because it involves a memory allocation every time you create it. So here is my new, before I did the optimization, I just had new delete, a new destroy of deleter, which calls malloc. And in the destructor, I would have to call free. So memory allocation is a slow process. Memory allocation in concurrent programs is a very slow process. So this is a significant drawback. The most common solution is what's called local buffer optimization. What you do is inside the class, you have a buffer, and you're going to allocate this. You're not going to allocate memory for it dynamically. You're going to construct this derived object in the buffer, placement new, which means also you destroy it differently. You just call the destructor. You don't deallocate.
Question.
Yeah.
So, doing local buffer optimization would involve that with any, even if I don't use deleter, I would still allocate the local buffer with
The local buffer is always there because the type of the class does not depend on the deleter type. Therefore, everything that is in the class, all its local data members, are the same for all deleter types. So yes, the buffer will always be there.
So I would kind of pay.
You would pay that price, yes, in the size of the class. Now, you may be placing the default deleter in there. There are some subsequent optimizations. So, for example, you can create a special version of it that is only limited, that you can only use with stateless deleters. It would be done at, so you would have to do it manually. You would say, let me try to use smart pointer with a stateless deleter, then doesn't have a buffer, and the compiler would tell you, no, you can't. Okay, then the compiler would tell you, okay, you cannot call your template constructor with that particular deleter type because it's not stateless. There will be some static assert there saying use the other one. So there are some games you can play, but fundamentally, yes, that buffer is always there. So the local buffer optimization also doesn't work all the time. First of all, the deleter may be too large. Whatever size, again, remember, the smart putter class does not depend on the deleter type, which means whatever size of the local buffer you decided, that's what you get. The deleter is given to the constructor, can be too large. Well, you have two options. It's a design decision. One is, and that's, for example, what std function does. It switches to dynamically allocated memory. So it has a condition check. If the function, in this case, not deleter, if the function is small enough, it puts it in a local buffer. If it's bigger, use dynamic allocation. You can choose in your design to simply forbid larger deleters. And it's a legitimate choice. You're basically saying that the slow path is not allowed, period. If you take that path, you probably want to provide a template argument for the size of that buffer so your users can increase it and use a shared putter with a bigger buffer for these applications. But like, it's a design decision, trade-offs. So my point is basically, don't dismiss that option. In some cases, it's a legitimate choice.
Could you just figure out the buffer size
From what?
and compile that?
No, then you're not erasing.
The only place where the deleter type is known, it's a constructor's template argument, not class template arguments. If there was a tool that basically does this global overview of all your compilation unit and says the biggest deleter in your entire program is this, therefore I'm going to change the default size on your class template to that. But we don't have that, and it's obviously very fragile because you might compile some compilation units, you write one more file to add to it, and you got a bigger deleter there, so even that wouldn't work. But fundamental problem is that deleter is given to the template constructor. The template and all of its data members are written before template constructor is called.
If I may add something.
Yeah.
Option 2 gets a lot less onerous if you build a view type that erases the buffer size. And so then you can just have as many of these as you need, and on interfaces that don't need to actually delete it, you just take the view type.
Well, it depends on what you mean by onerous. Now they are of different sizes.
Sure, but like you don't offer copy in the view type because it's a view, right? You only offer the non-regular salient operations, but everything else you don't.
But you still have to store the deleter inside the class.
Yeah, you store inside the actual class, but in the view type that only has a pointer to the actual thing, right? It knows the layout of every one of those.
Sure.
So
but the underlying smart pointers would be of different type. So you can do it. You can have it.
Sorry, this is a smart pointer. I know it's for management, but when you're erasing an actual interface, then you've got 3 functions you care about, and then the management, right?
Yeah.
So if the view just does the 3 functions without the management, then any interface that doesn't actually need the management.
The view would be the view would be simpler than the whole thing. Yes. So if you have like a smart pointer that actually holds the data, and then sort of smart pointer reference kind of thing that is used to access the objects, but not, well, in this case, the only thing that deleter does is actually invoked in deleter, so it wouldn't really make sense. But in like function cases, so if you could do it to std function, like there is a std function that actually knows how to delete and copy itself, and there is the callable view that only knows how to call it. So there you could do it.
Yes.
Yeah.
Function ref.
Sorry?
Function ref.
Yeah, okay, yeah. So high performance applications often use the option 2, where basically slow path just doesn't compile. Anyway, you can choose whatever you want. Another interesting thing about local buffer optimization is moving these objects. Where it's easy to move an object which has something that it points to. When you move an object with an embedded data, first of all, a move becomes at least partial copying. If you had a no-throw move, you might not be. If you have a no-throw move, it's good. If the move wasn't no-throw, you might throw from your own move because you're basically copying that entire object instead of just swapping pointers. Again, design decisions. Do you want to restrict this optimization to no-throw movable types, or maybe even to the trivially copyable and types? Implementations can handle all of this with appropriate runtime cost, design decision, whether or not you want to pay it always, pay it conditionally, or just refuse to compile and say, this is not acceptable in my application. So, type erasure using inheritance. At the point where the type is erased, the compiler instantiates a class that knows what the erased type is. The interfaces of this class don't know what the erased type is because there is a common type agnostic base. The mechanism through which you access the reification code is through the virtual function calls. So basically the erased type is encoded essentially in the v table, in the v pointer. The constructor template generates the correct derived object, correct by construction derived object, and so correct by construction virtual member function overrides for your current type. You cannot mismatch the reification function with the type you previously erased, like you could do it in C with sort. You could pass wrong less. Here you can't do it. So again, the erased type is hidden in the code. All relevant behavior aspects would have to be implemented as additional virtual functions. Let's look at the other one, the second way, the static functions. This technique is much closer to what straight up C implementation of type erasure. This is what it does. If we were using C, we would write some reification function that takes a void star, casts it to our erased type, because when we write this function, we know what the erased type is, and then do some work on this type. In C++, instead, we just generate this. We have a template with parameterized by this erased type. The interface is still type agnostic, so notice you cannot deduce this parameter from the interface, from the call. You have to be, when you instantiate this template, you have to be explicit about the type you're erasing. Inside, it's exactly what you would have written in C. The good thing about this function is you can assign any one of them to a function pointer that does not have this erased type in its signature, in its type. So no mention of T here. A refi function of my deleter is assigned to it but any my deleter would work. Assignment would work. If I call this function through this function pointer, I would get the static cast to whatever this type was. So this is basically exactly the C implementation of type erasure, only I use instead of writing myself these types for all the types I want to reify, I use the compiler to do it for me. Okay, so let's do it for smart pointer, and I'm only showing the type erasure pass. I'm ignoring all the smart pointerness of it. So first of all, we're going to have that function pointer. So I'm going to have that the function pointer. Sorry. Oops. It's I used to have a type alias for this, but it didn't fit on the slide. Destroy T was the type alias for this thing. So I have a function pointer. Now I have a template static function with the exact same signature. And inside this function, I cast to the deleter type, which is my template parameter, and I invoke that deleter on the object pointer. So this is my reification template. In the constructor, which is the last place, it's templatized on the deleter, this is the last place where I know what this is. I'm going, of course, to save the data pointer, and I'm going to instantiate this template, the invoke destroy template, on the deleter type and assign it to the function pointer. Again, the constructor is always the thing that ties this together, that actually generates the code which hides the actual type, the erase type, in the code and hooks it up to type agnostic interface inside my class. Okay, I got that constructor. I can do the same thing with the local buffer optimization if I want, instead of so if I need to save the state, if I need to save the state of the deleter, I can like use a dynamic allocation, or I can do local buffer optimization and copy the deleter in there. Whatever I want to do, I'm going to use local buffer optimization on this example. But if you want, dynamic allocation works the same way. In the destructor, I'm going to invoke the function pointer. That function pointer here. What it's actually going to call is whatever the constructor assigned to it. And that thing that the constructor assigned to it, the signature doesn't know what the deleter is, but the code that was generated does know what the deleter is. So this is how I call the function on the erase type. Again, I have to either handle all the additional features or assert that I don't need to. So obviously I have to assert on the size. If I'm copying this in a local buffer, if it's local buffer is just char array. So if I don't do anything special about copying or deleting it, I have to assert that they're trivially copyable. Deleters are trivially copyable and trivially destructible, which in many cases is fine. Often you have like stateless lambdas here, which are, or function pointers, which are trivially copyable, and member function pointers trivially copyable to trivially destructible. If it's not fine, if you actually need copy operation, you would have to play the same game again for every element of the behavior that you need to handle that depends on the type. You would have to create another reification template, which comes with a drawback in this case. Previously, it did, other than you having to write this code, there wasn't any cost. This time there is a cost. And the cost is you have to have another function pointer in your object. For each one of these static functions which you generate from templates, you have to have a function pointer. So if you're preserving, copying, destructing, moving, comparing, and plus your original action that you started with, you're now up to 5 function pointers. So that's a drawback if you need to preserve many behavior elements, many functions. On the other hand, it's the fastest for one behavior element. So, okay, so let's see what we've done here with this, with this approach. At the point where type is erased, unlike the previous implementation where we generated a specific derived class, we instantiate a static function template whose interface doesn't know anything about this type, but the body does. So there is usually a static cast in there. The body of the static function and the code that is generated from it knows what the erased type was. But the signature doesn't. Because the signature is type agnostic, we can invoke that function through a function pointer that is a data member of the overall class, and as such, it cannot possibly depend on the deleter, because remember, deleter isn't a template parameter to the smart pointer class, only to the constructor. Yeah, question? Template instantiations are all assigned to the smart pointer. If you have a stateful object that you need to store, you store it in a char array in a buffer, or you allocate memory and store it there. Again, the type of this buffer that you store your deleter in doesn't know anything about what's being stored in it. It's char star. Your generated instantiation of the static function template would have to cast that char star to the right type of the deleter and do its work on it.
Just a small note. We could use actually lambda without captures as well, because they are
You can pass lambdas to it.
because they are customable to function pointer.
You can pass lambda. You can pass lambda to it. Oh, you mean you can write lambda instead of? Yeah, it's an implementation thing, and then you can write lambda or explicit function. What doesn't matter. But lambda without capture will convert to that exact same function. So you're getting either way. You're getting the same thing. It's only the question of how do you want to write a static function, and static functions are non-member. The static member functions don't act like members. So how do you want to write a static function? Do you want to type a lambda and have it implicitly convert, or do you want to write a static function? What you get is the same thing, yeah.
So lambdas, you get the same result, right? But it blows the binary after linking because lambdas aren't equivalent, and you get ODR violations and fun things that aren't detected unless you're compiling with.
Well, it will decay to a function pointer.
Yes, but the problem is in different translation units, it'll decay to a different one.
Yeah, and every time.
And so you can deduplicate, whereas if you stamp them out with actual named templates, then the linker can deduplicate those and give you only one, right?
Yeah, so here, where is my static function? Here's my static function. So in every translation unit that instantiates this, you would get the same thing, and it's up to the linker.
The same symbol.
Yeah, the same symbol, and then it's up to the linker to either resolve them all to one or hide them or whatever it wants to do.
I've been looking at ABIs. The linker does not know how to do what to do here, because you get different counter values based on what you instantiated before in the translation unit. It's really hard to deduplicate.
But you won't get you don't get ODR violation with this.
You get undiagnosed ODR violations unless you're compiling with link time optimization, in which case the compiler is going to say, too bad, not doing it.
When you use lambdas.
No, I mean not for lambdas. For this.
For this, yes.
For this, you do not get ODR violations.
You get the ODR violation on the constructor, because you get different code for what you put into destroy. You invoke a different symbol, and those are not equivalent. They're IFNDR, ODR. They're ODR not equivalent, even though we all know what they are.
So, but you're talking now about lambda, not about the static function.
Lambdas decay to static functions.
Yeah.
And the problem with lambdas is that they're anonymous, and it's hard for linkers to deduplicate them, and
Yeah.
therefore you get ODR violations at usage spaces. Like, you need to be careful, is what I'm saying.
Yeah, lambdas have anonymous type, but with the explicit type, it's like any other template. Every time it's instantiated,
Yes, explicit naming is perfect.
Yeah.
Use names. Avoid lambdas and headers.
Yeah, with explicit names, you don't get ODR violation because every instance of that name has the exact same definition.
Exactly.
What you wrote. Okay. So let's see. So the downside. So this is the fastest path, but the downside is for every operation you want to support, you need another function pointer. So we're now going to look at the third option. And I call it vtable, you'll see why. To be clear, okay, I didn't invent any of this. All of this taken from the works mainly of Eduardo Magid, whose works are based on some of the earlier works by Arthur Adwire. And I'll have a reference later on the slide. There is a wonderful open source type erase package called Zoo that Eduardo wrote that does basically that. It's what I did is greatly simplified the quintessential part of it to explain to you what's going on. All right, so it's still going to be, even simplified to the absolute minimum, it's still going to be a sizable chunk of code, at least in terms of slideware, so we're going to have to look at it in pieces. My smart pointer class, so first thing I do is I declare inside this struct, and I call it vtable, and it has function pointers. All it has is function pointers. And it has one function pointer for each operation that I want to support that I deem relevant element of behavior. So if I wanted copies and so on, there would be more of these. I'm going again to focus only on two. More than two doesn't fit on the slide. Yeah, I have types for them, but function pointers. So that's the nested type. Inside my class, I have a pointer to an object of that type. Let's initialize it to null for now. Every time you see something like this, you're thinking, okay, memory allocation is about to happen. So I'm going to new one of these and hook it up to here. No, I'm not. So let's look at the second part. Now, the definition of vtable, you just have to remember it. It's that. So I have my pointer to a vtable, and now I have this template. This is the one that's going to generate the right code, but because it's parameterized by the deleter, but let's see what is it. It's not a function. It's a variable. I'll show you later what goes inside into initialization, but it's a template static variable. It has, regardless of the deleter type, it has that vtable t, which is that struct of function pointers. It has that type, matches this pointer. Now comes my constructor, and the constructor again is the place which hooks up the array's type with all the machinery that is going to hide it and execute it. So here is where the magic happens. My pointer is assigned to an address of this static variable. Okay, so let's see what this is going to do. So static template variable, I have this vtable pointer, vtable t pointer, assigned to an address of an instantiation of this template. So every time the constructor is invoked with a particular deleter type, it instantiates the template and creates a static variable. So this is an interesting case where my object, my class smart putter, has multiple static variables with the same name. I mean, the name includes the type, but like internally, I see them as this. But there is more than one of these. Depending on which constructors I use, this class has many static variables, all named vtable. There is another thing of static variables. Every time you use a regular static variable in your class, you have to define it and initialize it in a C file. You can't do it in just header, with some exceptions. Not for templated static variables, because obviously for templated static variables, you wouldn't be able to do it. Because in the header, you know when the compiler instantiates this template, it knows what deleter type is. When you write a C file, what are you going to put there? So the rules for templated static variables are different. Specifically, you don't have to define them anywhere else. This is the only place where they need to be mentioned. And yeah, it's a hell on a linker to deal with that.
Do you mean that the linker can fail? Or?
I have never seen it actually fail, but it's a non-trivial job that it has to deal with. I've never seen it actually fail, but it basically has all of these static variables, and unlike normal non-templated static variables, it doesn't have a single definition. It has to basically figure out where to put the single definition.
Just weak symbols. It's fine.
Yeah, so the linker, yeah, those, well,
Keep one.
It will have to keep one. I don't think the GCC does it anymore, but at one point they had a shortcut where they would actually stick it in the compilation unit, in one of the compilation units. But no, now it's usually just weak symbols. So
would this work even if you put a default there?
You'll see in a moment, but yes, it does work, and you'll see how, because that's exactly what I'm going to do. All right, so now I didn't show you what's in here. So now I'm going to show you what the ... is. So here is my template for my static variable. And inside that template, I have function pointers. Well, I mean, I must have function pointers. This is what, remember, this is what the vtable type is. It just has two data members. They're both function pointers. I have to initialize them to function pointers. So let's initialize the first one. I'll write another static function template. These are regular function pointers, not member function pointers. So I have to use either freestanding functions or static functions. I'm using static functions. Static function template that depends on the deleter. The interface is fixed. Whatever I put here as this destroy t and I put void star, this is what I have to say here. I can't say deleter here because my vtable t doesn't know anything about deleter. But I can cast from a void star to deleter star. So that's exactly what I'm going to do. And I'm initializing this vtable t with this aggregate initializer, which has two function pointers. This is one, and well, this is the second one. I'm going to invoke the destructor. And yeah, this is written for a local buffer optimization, so I didn't deallocate memory. If you wanted to deallocate memory, obviously you'll do it here. Okay, why am I not deallocating memory? Well, because I did, as I said, local buffer optimization. So I have my buffer, which means inside my constructor, I don't need any memory allocation for the vtable itself. This points to an instance of a static template variable. The compiler handles the memory allocation. It's somewhere. Yeah, there is memory associated with it. I'm taking address. I don't do any allocations for it, dynamic or otherwise. Compiler does it. It's somewhere. I can take an address of it. That's all I need. I do need to stash away the deleter. So yeah, placement new in this case. And of course, I need all the static asserts. If I want a dynamic buffer, I put dynamic buffer instead of the local buffer. Same thing. So the constructor does three things. And again, the constructor in the situations is always the place that ties all the different separate pieces of this type arrays machinery together, because that's the last moment in your code where you know what the deleter type was. So yeah, of course, store the object pointer, store the deleter in the buffer, and point the vtable to the correct, by construction, instance of this static variable. That's what the constructor needs to do. All right, so I've initialized everything properly. Now, in my destructor of the smart pointer, that's where I actually have to perform an action that depends on the type I just erased. No problem. I have the vtable pointer, and the vtable is a struct. It has function pointers, and I invoke the right function pointer for my action, which is deleting the object that the smart pointer owns. And then I invoke the other function pointer, which is deleting of the deleter itself. And if I need copies and so on, I have more of these function pointers here, and they're being invoked from copy constructors and all the other necessary places. The important part is Now, so this is very similar to what I've done before with static functions. In fact, my destroy, the function that I assigned to destroy and destructor were static functions, static template functions. The difference is, in my version 2, I had a function pointer directly in the object for every static function that I wanted to be able to use. This time I have only one pointer in the object. I have a function pointer in this vtable t, one for every action that I want to perform. But there is only one of these for any particular type, and the compiler generates it, and I don't have to allocate it. In my class, I only have one pointer to this vtable. Yeah.
Can you go back one slide?
This one?
Yes. Is in this approach, you need the buffer just because the deleter might have state?
Yes, you need the buffer only because the deleter might have state, yes. Or because you don't know whether it has state or not, because you chose not to ask that question. If you somehow knew that it doesn't, you could avoid the buffer. Yes?
Does making the vtable store the function pointers instead of having them directly in the smart pointer, adding that indirection, does it make cache misses more likely?
Yes, we'll actually see performance with benchmarks, and I'll run the live benchmarks for you for all three. So we'll be able to compare.
Isn't that exactly what the compiler is doing on the first option?
Yep. So I see the last line on this slide. This is exactly how modern compilers build their own vtables. So, well, they
modulo thunks. It's like there's additional polymorphic things that compilers stick into.
Yeah, there is more. Yeah, there is more stuff in there. But as far as the invocations, like just the part that leads you to the right function to invoke, that part looks exactly like that. You have function pointers somewhere, and that somewhere does not do dynamic memory allocations, just like we didn't. Compiler figures that, puts them in there, generates them at compile time, and your vtable, your vpointer points to that. There is more in that data structure than what we had. But as far as the function pointers, that's exactly the same logic. So if you wanted to do, like for example, if you wanted to do RTTI, obviously this, like you have to put something else into that struct. But if you just wanted to have a virtual function dispatch, and if for some reason you couldn't use virtual functions, this is exactly what the compiler would do as far as that dispatch, has exact same performance also. Like basically, other than, of course, compiler does it for you in one line. To do this, you have to have work. So like there is one other reason to not do it gratuitously, and that is that the compiler, under some conditions, can devirtualize your virtual function call, specifically if it sees what the object was constructed as. So if compiler sees that the object is constructed as this particular derived type, and then the base pointer, like the entire chain of existence of the base pointer is visible to the compiler, and here is the virtual function call, and the compiler ties together the moment of construction and the virtual call, the compiler actually can devirtualize the call, and at compile time, instead of using an indirection, just invoke statically the right function. I don't think any compiler would be able to unravel this.
They do it. They do it.
They do manual?
They constant fold the initialization, and then you've got a static table of function pointers. And as long as you constant folded the initialization, then you know exactly what you're calling.
But like the virtual,
it's the same thing. Like they do it.
I haven't seen it. I have seen devirtualization work in practice. I haven't seen this getting optimized. So like I tried it on GCC and Clang, and I haven't seen it getting optimized. In theory, it's possible, but for devirtualization is a pattern that they know. This one, they have to actually analyze the code to see.
It's a different compiler pass, but it happens sometimes. It's a different. It happens sometimes. I've seen them do it.
Okay, so the observation was that sometimes the compilers can do it. All right, so this is basically the essential elements of this vtable approach is, at the point where the type is erased, so at the constructor in our case, the compiler generates multiple functions that reify the types, and they're all instantiations of different static templates. The erased type is hidden in the body of each of those generated functions. But the signatures of all of them are type agnostic. I used, in my case, it's void star. Every time the compiler instantiates one of these templates, it saves it as it saves it into a function pointer inside a struct, and we call it the vtable. That struct is a templated static variable, which means I don't have to do dynamic allocations. It does depend on the deleter. The constructor instantiates it. The vtable pointer of my object points to the correct instance of that template. If deleter is stateful, or if I simply didn't optimize for stateless deleters, it's saved in a local or dynamically allocated buffer, and from this point forward, the deleter type is gone. It's not visible anywhere in the code, has been erased. All we have is signatures like some function of void star and char arrays. That's all we have. Until we start invoking the reification functions, which take void star and char star, but inside of their bodies they do casts to the type that they know. And how do they know? Because they were generated with that type. Same thing as C, except I didn't have to write them. I couldn't make the mistakes, compiler wrote them. So the machinery again hides the type in the generated code. That's common to all implementations of type erasure. The type is somehow hidden in the code that is being generated. The disadvantage is it's a double indirection compared to the previous implementation where we had a single indirection. Double indirection because I have a pointer to the vtable, and inside the vtable I have a function pointer, whereas before I just had a function pointer directly in my class. Advantage is my object has only one vtable pointer, no matter how many behavior elements I am abstracting. All right.
There's also one other big advantage. You get to control where the vtable pointer is. And if you put it at the beginning of your class, you actually get to zero it to like say there's nothing here. You don't get to zero a class with a vtable pointer. And that's a big deal for queues.
Well, I can still have a function pointer pointing to null if I want to.
Yes, but you can't have a vtable pointer to null. And you can't observe that.
In this implementation, if you really want to, you can, but I mean,
no, I mean in the class hierarchy version.
Oh, in the class hierarchy version, yes.
Vtable pointer, right?
Yeah.
So that means you can't use it as a flag also. And
that
actually really matters.
Yeah. In this, if you control it to like whatever you write. So if you wanted to have a code path where a vtable pointer is null, you could do it. Yeah.
Just 2 comments. For me, I see the second approach, like the C way of implement object-oriented code, and the third way, like the C++ way with the functions and have the virtual tables and etc. That's the first comment. And the second comment, you are type erasing the deleter,
yeah,
like the share pointer does.
Yeah.
But also the share pointers can also type erase the pointer. You can have a shared pointer void star void, so you can stick in pointers to int, to doubles, to full, to bar at the construction time, and the types erasure everything. Type erasure the pointer t is a void pointer, but then at destruction it will call the right destructor because at construction time the deleter knows the type.
Yes, I needed, obviously you can type erase multiple different objects, and you can even choose different implementations for different things you're type erasing. We're actually about to do that in one of our benchmarks. I did everything with just the deleter in a virtual pointer. I will show you the benchmark for that, but actually benchmark for stat function is more interesting, and there, yeah, I'm erasing the very thing that I'm calling. Okay, so the benchmarks. And yeah, I do have the code for it, and compiles and runs, and this goes the benchmark, so I'll show you the results. So what I'm benchmarking the deletion part, the creation and the deletion. So not use it as a pointer. Use it as a pointer, in this case, does not involve any type erasure. It's just dereference of the pointer, of the data pointer. So I'm constructing and deleting. Well, obviously raw pointer is the best, but it doesn't have a custom deleter. So I would invoke manually the custom deleter to use this raw pointer. Unique putter, very close. My own version of unique putter. So this is a non-type erased smart putter, pretty similar. Then we have the type erased version, and the static one, that's where I have directly in the smart putter class, I have one pointer, function pointer to the static function that does the deletion. It's a little faster than the vtable. So if you want to know the price of double in direction, here it is. In this case, I was only doing the small enough things to fit into local buffer, so optimization local buffer and local buffer only, meaning it will refuse to compile if it can't put it in local buffer, do exact same thing. And the vtable is kind of similar to the polymer. So these two are the inheritance based, and this one is the vtable based. Since you basically wrote, or I wrote in this case, what the same thing that the compiler does, they perform exactly the same. Shared putter pays the price of the extra allocation unless you use make shared, in which case it doesn't. If I simply use type erasure with dynamic allocation, I pay the same price too. So this is what the shared putter looks like. Now, the deletion performance of shared putters is usually not something you're overly worried. There are applications when you do, but typically for the smart pointers, you call through them or access through them data many times, and you delete them like once per many accesses. So usually it's the operator arrow performance what you care about, not the deletion. Well, let's look at the other object where you actually care about the performance of the type deleted, type erased execution path most of all, and that's the stud function. So I'm going to use the stud function, and I'm going to compare it with my own type erased version of the stud function. As I mentioned, here is the reference to the zoo. So how am I going to implement a type erased function? I'm going to combine two options. I'm going to use option 2, which is the static function pointer, for the critical path of invoking that function. I'm going to use option 3, a custom vtable, for everything else, copying, deleting, moving, all of that stuff. So I end up with 2 pointers in my object, 1 to the static function and 2 to the vtable, which in itself has a bazillion, however many I need, static pointers. And I'm not going to look at the performance of vtable because I'm only benchmarking the call, not the copying. I'm going to use local buffer optimization, and I'm going to restrict myself to the small enough types for which that function, which also uses local buffer optimization, also uses its local buffer. So I'm going to be fair in my comparison. Stud function, by the way, well, the standard doesn't say what the local buffer should be, or even that it should be, but at least like on GCC and Clang, it's 8 bytes, which is unfortunately insufficient for member function pointers. So member function pointers, even though they are like easy to copy and don't require any non-trivial deletion, they have to involve memory allocation if you use them with stud functions.
And it's also insufficient for delegates.
Well, it's insufficient for a lot of things, but basically function pointers and stateless lambdas are the only things that go in that local buffer, nothing else. If you write your own function, you can make it bigger. Okay, as I said, I'm going to ignore the whole copying moving for now because I only care about performance of execution. So I'm basically going to statically assert trivial everything. So just so I don't have to deal with it. If you look at the zoo, you will find that they deal with it, but that's like thousands of lines of code for them to deal with all the possible combinations. I just want the basic thing. Okay, so here is my template. It has a signature as its type argument, and yeah, it has parameters for type and alignment, which I'm going to ignore from now on. So I'll reduce my template to this. Notice that this is actually an incomplete type. This is all I'm going to say about this particular template. What I'm going to actually work with is a partial specialization that looks like this, which this is the signature, a result type of arguments. This partial specialization pulls out result and arguments for me. Poor man's reflection. In this case, actually, it works fine. You don't need anything else. Okay, I am going to use local buffer, and I'm going to restrict myself in my benchmarking to stud function also using local buffer. The function call is going to use the static function method. So here is my type for my executor function. This time I'm going to introduce a type def result of arguments, and I added one extra argument on the end. That's the pointer to the function object itself. Remember, my template is named function. I have a pointer to that function, if a function pointer. Well, to which function I haven't said yet. I have a function pointer. This is a data member of my function. And I have a static function template parameterized on my callable that I'm going to instantiate for in the constructor for every specific callable type. The only relevant behavior element of this callable is that I can invoke it with these arguments, and it gives me this result type, actually convertible arguments to these. This is my executor arguments, and I did say that I'm going to take one more argument at the end as a function pointer, so yes, here it is. What am I going to do inside? I'm going to restore or reify the type of callable. I know exactly what that is. Where I'm going to take so what am I reifying? I have this function, which is actually, at the call side, this function was simply this. This is a non-member function, so inside this non-member function, there is no this, but this is what it was. And I pointed to the space buffer, which is my local buffer inside my function object. And if I had dynamic memory, I would be pointing to that. And I'm going to cast this char star to my callable star, and I'm going to invoke it with arguments. That's all I'm going to do. All right. Constructor, again, is the one that ties together all the pieces. I am going to take the constructor, deduce all my arguments. Yeah, I have to do a little bit. I have to be a little careful to not try to make copies of references. So I need the types that the references refer to. I also don't want this to double as a copy constructor. So no copy. So copy constructor goes to its proper place. Oops. And this is where I instantiated the static function template and stored it in a function pointer. And this is where I stored my callable in the local buffer. Now, the last thing is the call operator. The call operator is where I get to invoke the function. So I have the call operator. It's a template on the arguments. I call the executor, which is a function pointer. The executor takes the same arguments, plus one more. I have to cast away the const, so I can make this thing const. But basically, I pass this pointer into the executor. Obviously, if you call it with incorrect arguments, you get really unfortunate error messages. So yeah, either static asserts or requires whatever you need to make sure that this actually matches the arguments of the executor. I'm omitting all that. I'm assuming that all the use is correct for now. Okay, this was the main behavior, the calling, the invocation of stud function. I also have to deal with copying and all that other stuff. That, at least in my case, is less performance critical. If it maybe in yours it isn't, but for me it was less performance critical. I mostly call these things. I copy them rarely. So I did the vtable for that. We're not going to measure the performance of that. You have seen on a previous benchmark it's a little slower. And I can just assert that it's trivially destructible, trivially copyable, and then I don't have to implement anything. Default. So now we're getting to the default. You can leave the default value of the executor pointer to null and check it at runtime. This is actually what stud function does, at least the implementations that we're using. The other option is it's never null, and initially it's hooked up to this. What does stud function do by default? If you don't initialize it, it throws. Nothing stops you from writing a default executor, which is a static function, and hook it up to your executor as a default initialization. And now if you didn't initialize it with any other function, it will invoke that. Never any conditional checks. It will just invoke that and throw. So this is what I'm going to do. Okay, ignoring the vtable, ignoring the dynamic buffers for now. And I'm going to do fair comparison where both stud function and my function use a local buffer. Okay, so the essential elements I already talked about them. Before I show you the benchmark, I'm going to show you what the assembly code looks like. So here is some function of like 4 arguments. It has a type. First, let's see what the assembly looks like of a function that invokes this. Looks like that. It just jumps to that address. Okay, let's see what stud function looks like. So I have the same function, the same type. Stud function of f is sf, and I have a function that invokes a stud function of that signature on the same 4 arguments. Okay, fine. I'll make it a little bigger. That's what the assembly looks like for stud function. Well, that's GCC 13. I mean, other compilers might do different things. GCC 13 did that on x86. Okay, I'm now going to use my type erased function. So my type erased function is just named function. Function of f is going to be ff. I'm going to invoke this thing. That's the assembly. Notice that normally when you call function, there is a call. There is no call here. What it does, it's called a tail call. There was already a call at the call side, and the return address was already placed on the stack, so somebody will have to do a ret. Well, who will do ret? Well, this guy does a ret. All I'm doing here is jumping to that without putting anything else on the call stack. So the ret, the return from this f, will not take me back here. It will take me directly to whoever called me. That's called a tail call. Okay, so here is the benchmark. Freestanding function. 25 nanoseconds. My function, this is actually within noise of the measure, 25.326 within noise of this measurement. Stud function. Twice as long. So yeah, that that whole extra assembly actually did matter. Yeah.
Which stud function did you use?
Whatever GCC 13 has as a stud function, that's what I use.
Strictly C++.
Yeah. So when you write stud function and you compile with GCC 13, whatever you get is what that is. No, not the. Okay. Now we're talking about indirection. So there are 2 more ways to do. We need to ask a few more things. Okay. So first of all, if I simply call that function through a function pointer, same time, what about the virtual function call? Same arguments, but just the virtual function call, same time. Again, in all of these benchmarks, I take pain to ensure that the compiler can't like devirtualize or optimize anything. The function I'm calling in a different compilation units. So there isn't like the compiler can't make any games. What if so this looks really great, and basically type erasure, as good as any other indirection if it's done well. There is just this one little thing that reminds you of the cost of the indirection itself. If you could inline this function, things would go much different for you. So this isn't the cost of type erasure. This is actually a cost of indirection. So two conclusion slides, 2 points. One is how it's done. C++ type erasure fundamentally is very similar to C type erasure. The type is hidden in some code that is generated in C by you, in C++ by the compiler, and correct by construction. There are several ways to do it. They all basically play the same game. There is some function somewhere which has a type agnostic signature and a type dependent body, and restores the types by some kind of casting. C++ just makes it correct by construction, so you can't make mistakes. In terms of the application, it's an abstraction pattern, or it's a decoupling technique. It does the abstraction or the decoupling at the cost of indirection. When properly implemented, it's as fast or as slow as pretty much any other indirection. You could use function pointers, virtual functions. They all basically cost you more or less the same. And all indirections have significant cost if you're using them needlessly. You can't beat inline functions for many reasons. On the other hand, if you need that decoupling, if you need the indirection, so the cost of the indirection cannot be considered. Basically, we're no longer comparing with inline functions, because inline functions don't solve the problem. So basically, we accept that we need an indirection. So now all solutions without indirections are off the table. At that point, type erasure actually doesn't have any overhead when it's properly implemented. As you've seen, it's as fast as any other indirection you can do. So in the sense, what's the overhead of type erasure? If you use it needlessly, a lot. Same for any other indirection. If you must use some indirection, nothing if you've done it well. Okay, done. And questions? Yes, please.
So in your timings, are those measuring in a way that the branch predictor could accurately predict where it's going, or in a way that prevents that?
Yeah. Okay. So the question was about branch predictors. Indirect calls are also, from the point, branch predictor, we think of it as sort of predicting conditionals. Indirect calls are also handled by the branch predictor if it can predict them. I'm always calling the same thing. So branch predictor in this case probably can predict everything. Now again, remember that the important part isn't that from this point of view. Well, if you want to know what the cost of indirection is, yes, it's important. If you want to know what the cost of type erasure is, you just have to make sure it's the same for all other indirections that you're comparing. So, like if you want to compare with virtual functions, the derived class type may be predictable or not predictable. Do a fair comparison, compare with a type erased destination that is equally predictable or non-predictable. In my case, it's predictable. Yes.
It's just I don't quite agree, I guess, with the measurement of a double indirection versus a single indirection where you have the pointer in the class, because it really depends on whether you're under cache pressure or not.
Well, it depends on whether you're under like very severe cache pressure. If you're calling it often, it will be in cache. If you're not calling it often, why do you care? If you're calling it often, it will be in cache, which will cost you something else. So you will evict 8 bytes from cache, for one of these, for a second function pointer. If you are under enough cache pressure that losing 8 bytes matters, then yeah, it would.
It's 2 cache lines.
Well, yes and no. The vtable pointer is in my object, so that I use that cache line, but I probably use it for a lot of other things.
But then the vtable is somewhere.
The vtable is somewhere, and that is a separate cache line, although its function pointers are all laid out, so all of its function pointers are there. So yeah, so I will, so the pointer that is inside my object, I probably will get without any cache misses because I already worked on the object, it's probably there. And even if I have a cache miss, I would have had it at some point anyway. The second indirection to the vtable, that's the one that matters. And yeah, if it would be worse if you, like, for example, if you had a cache miss every time, which means you're churning the cache so rapidly that even though you're calling this frequently, you still get a cache miss every time. That would hurt. If you're using inheritance, it will behave exact same way.
Exactly. It's just, the point is, if you have very heterogeneous collections, then investing into pointers inside object might be worth it.
You would pay in size, but you may gain performance.
Yeah, exactly.
Yes, question in the back.
So you can actually play a bit of a trick here in that you don't have to, if you have multiple functions, you don't have to use a vtable for it. You can just have one function pointer with an extra argument that says which function you want to call.
But you would have a conditional.
Yeah. The thing is, that's very predictable, and it would be in the instruction cache rather than the data cache.
Yeah.
So that would be like, you would have essentially one indirect call, and everything else would be predictable and potentially even inlined in that function.
That is what I've noticed.
So you can avoid the overhead of like virtual calls that way.
That's the opcode approach
Yeah, so
okay, I missed that.
so yeah, so you can do it, but you will be taking a conditional instead of an indirection. Whether that's better or not, well, depends on what else is branch predictor is doing. If branch predictor is basically an associative cache. If you filled it with other stuff, predicting conditional system may be expensive. If you didn't, maybe cheap. Yeah.
I mean, with that approach there, right, especially with like ST function, right? Like you could mark your branch for your destructor unlikely, right? You're only going to get. Which
has absolutely no effect on anything now. The built-in expect likely, expects unlikely. All it does, you can look at that generated assembly. If in an if-else, or in a conditional which comes from if-else, it rearranges the code between the if branch and an else branch. It swaps if and else branches. On the assumption that a forward branch is always taken, if there is no other. Basically, a forward branch is taken if the branch predictor doesn't say otherwise, and the forward branch is not taken, and the back branch is always taken. The back branch is for the loops, where you jump back to the beginning of the loop. The forward branch, the assumption is it's not taken. Matt Gottball did a lot of study on this, and he found that in all the processors after the Arrowdale core, static prediction doesn't do anything. So that built-in likely, built-in unlikely, it still swaps your if-else code. You can look at the assembly. Now, it seems like some people, sometimes you can find it emits hints. There are no hints, at least on x86, there are no hints to the predictor. It emits exact same instructions. You can look at the instructions. All it does, it swaps if and else. And at least according to Matt, Arrowdale was the last Intel core on which there was an observable difference on the static predictor, if the branch predictor is uninitialized, which way it guesses. After that, makes no difference whatsoever. And Arrowdale is what, 12 years ago, 10 years? It's a while back. It's not one of the recent cores. Okay, any other questions?
So
yes.
On that note, if like marking things is likely and unlikely does nothing, how do you make it? Like how do you provide hints to the branch? Or do you just assume that?
There are opcodes, but they're knobs, like they don't get treated.
Yeah. So it predicts it based on order. It ignores all hints. You can give it a hint, but it ignores them.
Yeah. So there is no basically. So Intel has not documented, and AMD also has not documented, at least in any public documentation, what the static, we're talking about, so dynamic branch prediction is based on learning. That's what branch predictor does. Static branch prediction is based strictly on the code of the program. Intel has not documented, at least publicly, what their static branch predictions algorithms are. So, it will invoke speculative execution, so it will do something. What they do, we don't know. like Matt couldn't find it, also I couldn't find it. They do something. If you knew what it does, maybe you could arrange your code to match it better, but we don't know what they do. Yeah?
My recollection is like there are opcodes for giving hints to x86 on what the prediction is, like what you think will the static prediction should be, but it doesn't actually like use them. Like I think in recent processors they either stop using them or something like that.
Well, I know that GCC and Clang do not emit anything other than the code that's supposed to be there, and so you can diff the assembly from built-in, likely to unlikely, or to swap the, I think it's built-in expected 0, 1. You can diff the assembly. You will see that there is nothing extra emitted, just the two chunks of code are exactly swapped.
Yeah, I think they don't emit it because it's not really big.
So maybe there is. I don't know if there is an opcode that actually works. I know that neither GCC nor Clang nor Visual Studio emit it currently, because that I would see in the assembly. If there is an opcode that none of these compilers use but would have worked, I didn't find that in any public documentation, but maybe there is one. I don't know. Okay, any other questions? If not, well, thank you all for coming. This was